Hello, welcome to the first video on Gauss's law for electric fields. So in the next couple of videos in this series of Gauss's law, we're going to look at the applications of Gauss's law, and we're going to also, of course, look at the equations in integral and differential format. So in this video, we're just going to look at the basics of Gauss's law in integral format and see if we can derive Coulomb's law. So let's get started. Gauss's law for electric fields, okay? We have the surface integral, okay, of our electric field, which is a vector, dotted with dA, is equal to Q divided by epsilon sub naught. So what does this mean? So Q, first of all, is the charge, okay? It's a point charge. So let's draw a diagram. So we're going to have a point charge, let's call it Q, all right? And so what we can do with Gauss's law, so we can imagine an imaginary sphere around this point charge, okay? It's called a Gaussian sphere. So just pretend this is a symmetric sphere around our point charge, Q. Okay, so obviously Q possesses an electric field which is right angles to our surface, because the surface, of course, has unit vectors n that point at 90 degrees, like that, okay, at every point. Okay, because the sphere is uniform, the electric field is always 90 degrees to the surface, okay? Now, let's just pretend it isn't in this case, okay? If it's not, there's going to be an angle, okay? We're going to call it theta, okay, in which it is 90 degrees, okay? So imagine this is the electric field, okay, coming from the charge. This is called the electric flux, and it's an angle theta to a line that is perpendicular to the surface. Okay, of course, the electric field is 90 degrees, okay, in real life, in actual situations. Right, so the electric field, okay, E, of course, that's uniform, okay, it's a constant that's coming out the whole charge and permeating through the surface, the imaginary Gaussian sphere. So what's E dot dA, first of all? Well, we can start with dA. dA, okay, as you've guessed, is an infinitesimal surface element on our Gaussian sphere, dA. Okay, that points 90 degrees from the surface with unit vector n. Alright, so what we can say is dA, okay, or vector dA, or vector surface element, is equal to dx times dy times the unit vector, okay? So what's E dot dA? Well, first of all, the electric field multiplied by an area is the electric flux, okay? So therefore, if you do E dot dA, that's the electric flux on an infinitesimal area. And if we integrate that small electric flux, we get the total electric flux on our Gaussian sphere, okay? So E dot dA, E is a vector, dA is a vector, we're going to take the dot product. So E dot dA, okay, this is simply equal to E, which is a constant, it's uniform, multiplied by our dA, multiplied by the cosine of theta. This is theta. Now, if you remember, in real life, the electric field is 90 degrees to the surface, so theta is, of course, 0. The cosine of 0 is 1. So therefore, the dot product between E and dA is simply E dA. Okay? And of course, we take the integral, the surface integral, which means we have an infinitesimal surface element and we integrate it around the whole Gaussian sphere. It's imaginary in this case. So the integral of E dA. So because E is uniform, it's a constant, we can bring that outside the integral, and we get E integral dA, which is of course equal to your electric field multiplied by your area, and of course that's equal to the charge enclosed, okay, enclosed in this Gaussian sphere, divided by the permittivity of free space, epsilon naught. Right, so what's A? A is of course the surface area of our imaginary Gaussian sphere. The surface area of a sphere is 4 pi r squared. So we get E multiplied by 4 pi r squared is equal to Q divided by epsilon sub naught, like that. Okay, and we can rearrange to find E, the electric field strength, and that of course is Coulomb's law. E is equal to Q divided by 4 pi epsilon naught r squared. Okay, and we can simplify that. Okay, what's K? Well, we can say that K is 1 over 4 pi epsilon naught. Okay, therefore E is equal to KQ over r squared. And that's a very common formula that we see in A-level physics, for example. Okay, so that's Coulomb's law derived from Gauss's law, okay, in integral format. Okay, so that's the basic concepts of Gauss's law in integral form. Okay, very, very simple. And so in the next couple of videos, we're going to look at applications of Gauss's law in the real world. And we're also going to look at the differential format of Gauss's law, okay? So that will involve probably concepts on calculus through like the divergence theorem and so forth. Alright, so I hope that made sense, and hopefully I'll see you in the next video.